Welcome, everyone. Wow, that light's getting bright. It's hard to see you all. So I should probably start by saying that my name is Steve. I work for a company called ThirdChannel, located in Boston, Massachusetts, in the USA. I'm here today to talk about processing large amounts of data within your Spring application. A little bit different from the Spring Dataflow that we just saw earlier. For those of you who are familiar with Cassandra or Spark, you probably realize that there's going to be lots of talk about NoSQL today. And I should probably start out by saying that I think relational databases are fantastic. All this stuff that you're about to see, you may never actually need to use. There was a talk yesterday about Juke, which is one of my favorite tools, because I really think that working directly with SQL is a great skill to have. I think working directly with SQL makes you a better developer, makes you a stronger person. My absolute favorite data store in the world is Postgres. It's got full JSON search, full text search like Solr. It's fantastic. However, sometimes your data goes, and your needs go beyond what a relational system can provide. As your data grows larger, you have to start doing things like sharding. I try and do data replication, master-slave, et cetera. The more data you acquire, though, it's harder to analyze within a relational model. So, this talk is aimed towards those of you who have an unusually large amount of data saved that you need to process, or those of you who expect to start receiving large amounts of data very soon. If that helps, that was me. I'm a guy working for a group whose data needs were not entirely being met by a pure SQL relational solution. Our amount of data ingestion was growing at a relatively unbounded rate. Maybe not a massive amount in terms of your big data terminology, but for every one of our clients, we start to ingest gigabytes of data per week, which again, not that much, but for every client, it adds up. And we needed a solution that could ingest, process, analyze, and then spit out meaningful information at a decent rate. Basically, I needed a modern big data ingestion pipeline system with a component for handling an ever-increasing amount of data in a reliable way, and a tool for processing it. And I'm a big fan of the Spring ecosystem. I will add that, though, that the term big data annoys me for some reason. That's why I keep doing the air quotes. You probably won't hear me say it again, hopefully. I'll wait for y'all to take a photo. I thought this was pretty funny, too. Also, I'm sorry that we have Trump. Anyway, so I looked at what options were available to me at the time. I settled on a pair of technologies from the Apache project that are becoming increasingly popular in the big data space. Yeah, there it is again. I hope to share them with you today. So today, we're going to talk about each of these tools individually. We'll talk about what Spark is, what it does. We'll talk about Cassandra, where you might want to use it. We'll talk about what it's like with Spark and Cassandra together. They actually have some interesting mechanics that allow them to leverage each other's abilities in a really excellent and fascinating way. And then we'll talk what it's like to actually work with these tools, how to integrate them in your Spring application. And then I've got a bit of a demo that illustrates some of these techniques. It's well, we'll get to it. So Spark, has anyone here heard of or has used Spark before? Again, it's a little bit hard to see hands, so okay, great, thanks. So Spark is a distributed execution engine for processing large amounts of data. And it's fast. One of the fastest known general purpose tools for processing large amounts of data. Spark first got notoriety in 2014, where it won this data sorting competition called Gray Sort in the Daytona category, meaning that it was it's like a race car analogy, so it's like a hardware stock software. They used Spark, and the team that won sorted 100 terabytes of data using commodity hardware on AWS, specifically 206 EC2, and I can never remember this acronym, I2 8X large. So expensive machines, they're very large to be sure, but using 206 of them, they were able to sort 100 terabytes in 23 minutes. The previous world, I mean, if that doesn't seem impressive, the previous world record was 72 minutes using Hadoop, and it took them 2,100 nodes of the same type. So this means that Spark sorted the same data 3 times faster with 10 times less power. Very impressive. And all the sorting took place on disk using Hadoop's file system, without using, and you'll find out why this is important later, without using Spark's in-memory cache, which could have saved them even more time. So I mentioned Hadoop. Now why exactly do I keep bringing that up? It's hard to avoid comparisons. They're both big players in the big data space. Hadoop, they're a little bit different though. Hadoop is essentially two tools. One is the MapReduce functionality. That's probably why you might have heard of it. It also stores data on disk using their own technology called Hadoop Distributed File System. But Hadoop, for every MapReduce step, Hadoop has to write every stage of the transformation to disk and then reread it every single time. Spark, on the other hand, is basically just the execution engine. It has no inherent storage mechanism, and it offers many more operations than just MapReduce. If you've used RxJava or Project Reactor or Java Streams, it'll seem very familiar to you. And its big selling point is that it does not write everything to disk periodically. It is reliant on storing all of its operations distributed in memory in your cluster. Before I go further, one quick tidbit that I think is pretty interesting. So Spark was created as a secondary thought. So it was created by the Mesos team. So Mesos came out of Berkeley in this white paper that this team put together. And some random line in the project, they mentioned that, oh, by the way, so we've been working on this distributed management system called Mesos. But to test it out, we decided we'd build this little computation thing called Spark. So they thought, well, while we're building Mesos, let's also create the fastest general-purpose distributed computation engine the world has ever seen. No big deal. So what does Spark physically look like in your environment? How is it laid out? So this is an architectural diagram from the Spark website that gives you an example of what a Spark cluster might look like. So you have one master node known as the cluster manager, or sometimes it's called Spark master, or what have you. And so if you need to do work, you submit jobs to that cluster manager or the Spark main. And the submission process is typically done using an object called a Spark context, or the Spark context, which is generally created or instantiated within an entirely separate driver program. This driver program is external from the Spark cluster, but its Spark context receives responses from the cluster that it can work with and return data back to the driver program and then ultimately to you. So one easy way to think about it is I have my app, my Spring app, which instantiates a Spark context bean. Where when appropriate, I submit work to the cluster via my Spark context. I asynchronously wait for my results and then handle them appropriately. Working with Spark is deceptively simple, I think. From a programming standpoint, it adds two main objects for you to work with. The Spark context, which we already discussed. You operate and execute and submit jobs through it by calling methods on it. And then all operations that Spark does is performed against a type of object called an RDD, or Resilient Distributed Dataset. Now, RDDs are interesting because it's an immutable data structure that supports parallel operations. RDDs can only be created by performing actions against existing RDDs. They are reusable and composable and cacheable, which is interesting for reuse. But what is it like to work with? So here's a very simple example of an RDD in action. So that first line, there's a underlying functionality in that grab raw records method, which is basically fetching data from disk and then putting it into an RDD. And now once it's in the RDD, it gets distributed out amongst all the nodes in your cluster. And so that symbol results is now a representation of several Java objects distributed out amongst the cluster. Then when I call map, I then perform a transformation on those records, and then I grab the value out of them and then save it into another RDD of type double. So now I have a bunch of doubles distributed out throughout my platform. And then I call reduce, And then that coalesces the objects, or not coalesces, but brings them together amongst all of the nodes, performs a calculation on them, and then you'll notice that I'm not saving it as a RDD, but as a double, which basically means that the operations then go back through the context back into my class. So map and reduce are, again, just the basic building blocks of Spark, but there are many other ones. You have way more than MapReduce. Again, I don't know why they've listed them again, but you have MapReduce. You can aggregate things, you can filter, you can flat map, join. Again, if you've used RxJava or Project Reactor, it's all very similar. This is an example from the demo code I'm going to show you in a little bit. It's a little bit more obtuse, but this is an example of Spark joining different RDDs together, and we'll see why this is important in a minute. But I can take two different data sets and then join them together based on some operation, which is a very useful thing, again, as we'll see soon. But essentially what I'm doing here is I'm joining three different objects together, and then I'm mapping the values down in the end, and then spinning the results back, and then, well, we'll get to it. It's a lot of code. I don't want you to read it. There's a lot of, like, Scala tuples and things in there. Spark is somewhat infamous because it's got several additional modules that you can work with it besides just the basic Spark core. Two of the most important ones, I think, are Spark SQL, which is it's cool, but not as useful as you might think. So it adds this new object called a DataFrame, which allows you to execute SQL queries against that DataFrame, which is great, right? I have my relational data set, I turn it into a data frame, and then I can select star across it. But if you see, I'm typing raw SQL queries. And again, like I said, I'm a huge fan of Juke with type safe and everything. And I've not been able to find a way. One question that I haven't had a definitive answer to is does this allow connections over JDBC? There appears, it doesn't look like you can, which means it reduces its usefulness to me right away. But I think it's far better, easier, and more productive to simply emit the results of your Spark jobs, your RDDs, into an additional external relational database and then query them from there. A second module, Spark streaming. This is, you may have heard of this term before. I mean, it's becoming fairly famous, especially when you hear it mentioned in the same breath as Kafka. You read articles about people who are pulling streaming data off their Kafka stream and ingesting it in real time in their Spark cluster, and that's great. All it really does, though, is absorb events over the wire via a window function, and then instructs your Spark app to process each window of events individually, which is great, don't get me wrong, but I don't think it's entirely necessary for most workflows. For example, I could simulate Spark streaming with RabbitMQ with an appropriate quality of service label, and then send that information to Spark, and then perform my own window function on it if I needed to. So that's a brief summary of Spark. I mean, we could spend 45 minutes on it just by itself, but we got a lot more stuff to talk about. So, Cassandra is up next. Now, let's say, absolutely fascinated with how, with the different operations and methods and ways that Cassandra operates. It's really interesting. So and again, is anyone here actually using Cassandra or have played with it at all? Yeah? I think it's fascinating. For the most part, I don't think you all will ever really need to use it. I mean, it's a very specific use case. It's a NoSQL data store targeted towards time series information. It was made. It comes out of Facebook. It was open sourced and made an Apache project in 2009. What's interesting, though, is that there's some big names that use it exclusively. So Netflix, for example, last I heard, uses it for all their data. And reportedly, Apple is the biggest known user of it in terms of the most number of clusters and nodes running. So it's very intriguing, right? So all these big companies are taking heavy advantage of this thing. So why do they invest so heavily in it? And hopefully we'll see a few reasons why it's so interesting. So not only is it a NoSQL data store, but it's a distributed NoSQL data store, and that's its big selling point. But one of the big features of that, it has a deterministic distribution of data. So you'll often see Cassandra clusters drawn out as a ring of nodes, and people will sometimes say, not cluster, but my Cassandra ring. And so this is likely due to how Cassandra stores your data. We'll describe this more in a bit, but Cassandra forms a token ring. It's a bit like a hash table, and assigns ranges of these token values to each of your nodes. Now this is a little bit misleading because one of the key algorithmic bits here is that it doesn't give you an orderly range of tokens. Each node says, I'm taking, however many nodes divided of random tokens. So they lay claim to a certain set of token ranges. And then when a request comes in, there's no master node. So every node knows what the other nodes are responsible for. So when a value comes in from a user to, in this case, node 3, and the node that receives the information hashes the incoming data to find what's called, or hashes what are called the partition keys to figure out which token it should be assigned to. And it may be node 3 that's supposed to receive that data, but it may not be. So then node 3 will then shoot it over to the appropriate node that's responsible for that token. Cassandra is capable of extremely high replication. So what I was showing you, that slide back there was basically a replication factor of 1, which is not recommended for production use at all. So here's a diagram. It shows a basic ingest flow of data using a more common replication factor of 3, using a consistency level of what's called quorum. So basically what's happening here is the quorum consistency level says that the cluster will acknowledge to the user that it received the data when a quorum or a majority of the nodes have received the response. Now this is essentially eventual consistency. So what's happening here is that the user writes some information to node 5. Node 5 says, great, I'm not responsible for this. I know that node 6, node 1, and node 3 are all assigned to it. The data is being replicated 3 times throughout the cluster. So each one of those is supposed to get it and write it. Node 6 writes and acknowledges in 2 milliseconds. Node 3 writes and acknowledges in 25 milliseconds. Node 1 is being a slowpoke and does it in 200 milliseconds. But the user gets a response at 25 milliseconds. Node 1 will eventually be consistent with the rest of the nodes, which is very interesting, I think. The nodes will also, and this is the official term, gossip with each other. So if for some reason node 1 failed to write, node 6 and node 3 will eventually let it know that, hey, you were supposed to receive this. Please write and update this particular record. One of its biggest features, I think, is that this replication can be extended across data centers. And this is, I think, the biggest reason why people choose to use Cassandra is that it's very, very easy, if I'm a user in US West 2, to have my data eventually be streamed to US East 1. And we're talking, when I say eventually, we're talking fractions of a second here. But this is extremely easy to set up and configure, and very reliable. And by reliable, I mean Cassandra has extremely high durability. So if one of these nodes in the cluster goes down, so node 6 for some reason just dies, node 5 was supposed to shoot information to it, and it sees that node 6 is down, it will wait, and it'll hold on to that information and it'll keep checking to see if node 6 comes up. When node 6 does come back up, it will then, hey, here's all the data you missed. If for some reason node 6 does not come back up, then the cluster now realizes that it needs to be of 5 nodes, and it will reshuffle all of the tokens that 6 was responsible for and redistribute all that data, which is interesting. But that will only work if you had two other replications. Another big factor, and the reason why we went with Cassandra, is because it offers linear scalability in terms of performance. And what that means is that each new node that you add to that cluster results in an effectively linear increase in performance. You've increased your storage space by the capacity of that node with no loss in query performance. And again, the data location is deterministic. So when a new node is added to the cluster, that node chooses some random number of tokens to become responsible for, and then tells the other nodes, hey, I'm laying claim to these tokens. And then This is much more elaborate with replications and things. This diagram assumes a replication factor of 1. So when node 4 comes, or node, oh, that's supposed to say node 5. So when node 5 comes online, it will basically lay claim to all these tokens, and then the other nodes will start streaming the data to it. Meanwhile, they'll still answer queries for the tokens that they were responsible for until node 4 has finished receiving all the information. So this can be done without breaking the system down, although you'll likely notice some slowing in query time because the resources are being taken up to redistribute and rebalance the data. But this all happens automatically. It's very, very cool. So let's talk about the data model. So that's the architecture, the infrastructure of Cassandra. But what exactly is it? So Cassandra is, while it's NoSQL, it's also a column-oriented database. A column-oriented database is, like you might think, data is stored within tables by column. This differs from traditional MySQL or Postgres database that you might be familiar with. With these systems store data in tables by row. So column-oriented databases can, in certain cases, extract information more quickly than row-based, especially, and this is with very large data sets. And that's what Cassandra is, a very large data set. Why? It's very subtle. When row-based systems need to find a particular set, a particular row or set of rows containing a certain value, they will need to scan each row to look for that particular field. So if I'm saying, select star from people where last name is Pember, it's got to look through all the rows where the last name is Pember, identify them all, and send it back to you. Now, this is why you typically need to index your columns to skip that table scan. So when you create an index on a column, that basically tells the query that creates a structure on disk that is the row IDs with all the different values. So that when I query for the last name, it looks at the index first, finds all the row IDs with that matching value, and then just grabs those rows directly. So when you query, you're effectively doing multiple disk operations. Got to find the index, grab the rows, et cetera. And so one question you might have then is, isn't a column database just one that has indexes on every column? And so again, it's a very subtle difference. And I don't think I'm even smart enough to understand it. But what a column database does is store all values for each column and then a list of the row IDs. So if you're doing in a row-based database, you've got to scan the entire index to find all the matching row IDs. In a column, you just find the value, and then you immediately get all the row IDs, if that makes any sense. So if you have a huge data set, the column-oriented can be faster because it finds the matching column value first, and then instantly knows all the rows. But a row-based has to look through the entire index. Again, it's subtle, and it really only offers you a performance gain when the index gets really large. That said, Cassandra is very SQL-like. So it's based around a data structure of what's called a key space, which is roughly equivalent to a database. It also has tables, which are technically what is known as a column family, but they use the word table. When you create a key space, you set its replication factor. Generally, it's a good idea to keep that number odd, and never, ever in production make it a 1. You want to at least make it something like a 3. The more money you have to throw at building up your cluster, the higher you can set that value, can generally offer more resiliency and durability. But here it's 1, just for demonstration and for dev purposes. Note, when I'm creating my table, the primary key line is a little bit different than you might see in like a MySQL or Postgres table. So the primary key creation allows me to specify what are called my partition keys and what are called group keys. So the first value or set of values, here I've wrapped symbol in parentheses. I could put a couple values in there. But here I'm just partitioning on symbol. Now what that's telling Cassandra to do is to deterministically save all values that with a particular symbol into a particular token or into a particular node. So basically all records with the same symbol will end up in the same node, or if I have higher replication factor, the same set of nodes. The remainder of the keys in the primary key are known as the group or the cluster keys, and these determine the location of the data on disk. And so this is where it gets a little bit interesting, because you want to have appropriate group keys in order to minimize the data seek time when it's reading off of the disk. So this is generally for these particular values, you want to set things that are naturally close spatially. So time is often a good one. So I can write on my records in terms of when they occurred, and then I can query them by that time, which leads to querying. So Cassandra is, you type just like you would SQL, select star from X, group by, et cetera, et cetera. But there's a few interesting limitations that can be frustrating at times. So all queries where you do a where clause have to include the partition key, have to include all the partition keys. So if I were grouping by, or if I were partitioning by symbol and by year, for example, all my queries would have to be by symbol and by year. And I can only order by anything I've identified as a group key, because again, the data is all saved in disk close together, grouped by those order keys. So it would be non-trivial to allow you to be able to group things that when the data is not close together on disk. And so that leads into one of the more interesting bits, is that you really need to think about your data model when you're building up your table in Cassandra. So again, your partition and group keys are super important. You want to choose proper partition keys to encourage even distribution of data. For example, I could partition all of my data just by, say, a customer ID. But that's rarely encouraged, because if I have one customer who's super active, all of his data is going to be located on node 3. So that particular node may be getting much bigger than the rest of them. So it's a fine art to figure out how to properly evenly distribute the data. I mean, it's generally in production you'll end up having several, one or more, or at least two, let's say, partition keys in order to distribute out evenly without overwhelming one particular node. Which leads into another interesting bit. So in the Cassandra world, it is totally okay to have highly denormalized data and to duplicate that data in a variety of structures for effective querying. So for example, I've got two tables here where it's a list of movies by release date and then a list of movies by rating. All the exact same fields, but the primary keys are different. So in the first one, date is the partition key. So when a movie comes in, it gets all movies of a certain year are going to be saved on the same node, and then grouped by title. And then I have movies by rating, where all movies with the same rating are going to be stored on the same node and then grouped by title. Does that make sense? So that allows me to effectively query by rating or by date. Now the reason for encouraging highly denormalized data recreated in different ways is that Cassandra is very limited in terms of what it can do. For example, you can't do joins. You can't join across tables. Until recently, there's been very few aggregation functions, like sum, count, max, etc. So, I mentioned earlier, Spark has joins. Cassandra does not. Spark has no data store. Cassandra is a data store. So let's merge the two, and we'll see these tools are very popular together. So I know I've been telling you how great these tools are, but they each have their weaknesses. Again, Spark, just an execution engine. There's no data store. It relies on some other mechanism for storage. Its API has no real method of querying. The Cassandra, again, the general weaknesses of NoSQL apply. One of the worst here being that Cassandra, again, doesn't allow for joins across tables. It's very light on aggregation functions. But together, they reduce each other's weaknesses. So I can filter on the server side with Cassandra, thus reducing the data that goes out and gets distributed. So instead of loading the entire data set, I could just say, grab all movies that occurred in 2017 and distribute that out. Without that ability, Spark would have to look at all movies on my data store in order to process and filter down the appropriate result. Cassandra has no method of joining, but if I bring up multiple data sets or if I bring up multiple tables into memory, Spark can join those together and then find meaningful results. In fact, the pairing of those two weaknesses together has resulted in whole companies being formed just to harness the power of these two tools merged together. So most prominently is a company called DataStax, which if you Google Spark and Cassandra, nearly every result will be some sort of DataStax company giving a presentation or blog posts or documentation. Maybe this talk will come up there too. There are others. There's a company called InstaCluster, which is their whole business is managing a Spark and Cassandra cluster for you. There was another company called TupleJump. I don't know, but they were just acquired by Apple, and I'm sure there's plenty of others. DataStax, again, they've been big in this field. They've really been pushing these two tools. They've released an open source connector library between Spark and Cassandra, which I'd consider mandatory usage. I should probably point out Scala. So the group that made Spark, like most academics, chose to go a pure, highly functional route, and so they built everything in Scala. So the libraries in Scala, working with Spark, you're going to see a lot of Scala code. But one of the great things that this connector does is give you a lot of raw Java adapters that you can work with instead. So you can write all of this in nice, plain, easy-to-read Java. The connector gives you the ability to load data directly from Spark or from Cassandra into Spark by mapping it into POJOs, and I can save data back from Spark into Cassandra with those same mapping functions. And it also offers some other really smart algorithms for how to extract your data in a very highly local fashion, which we'll see in a second. So when setting up Spark and Cassandra together, your cluster design is going to change a little bit. So this is a single node in a Spark Cassandra cluster. Each node within a Spark Cassandra cluster is going to have one Spark slave process and then one Cassandra process. There's a lot of resource considerations to consider when working with these. They're both resource hogs, so this makes it a little bit tricky. So it's recommended to give Spark Slave one virtual CPU thread, and then Cassandra to give one CPU thread, and then allow them to share the memory on the system. It's highly configurable. Each of these tools have configurations where you can say how many resources they're allowed to take, and that's one of the first things you need to worry about. So one question is, why do I need to put my Cassandra and my Spark, or have a Cassandra and Spark process on each node? And so it brings the notion, the concept of data locality. I don't know if anyone's heard that term before, but it basically it means that I should be working with data that's highly local to my particular system. And by having Spark and Cassandra using that connector allows me to take full advantage of the distributed nature of Cassandra's token hashing. So a quick example. So if I have 3 nodes, a query comes in. One of the nodes also has to have a Spark master thread. So node A has, not only does it have a Spark slave and Cassandra, but it has Spark master. So when a query comes in through my Spark context, it gets passed to the Spark master, which then distributes that work out to each of the slaves in the cluster. The slave spins up a Spark executor, which uses a thread, and that's another resource to consider, is how many threads do you allow each Spark slave to run? The executor then, when the cluster starts up, it monitors the cluster so it's aware of which tokens belong on each cluster. So each slave knows which tokens its Cassandra process is responsible for. So when a query comes in and you say select star from blah where year equals 2017, the slaves are smart enough to only query their local Cassandra instances for the data that they need. Does that make sense? So in this particular case, In step 2, the query goes out to each of the 3 nodes, but only B and A know that they have the data necessary, so only they pull data up into the Spark slave and then distribute that calculation out amongst the nodes. Now, what this effectively saves you is network traffic, and it speeds up query time because it's essentially just doing a localhost query to disk and then sharing that information. And I find that absolutely fascinating. It is, of course, considered good practice to use many more nodes in a cluster than just 3. So I put a link to a white paper at the end of this talk that Amazon put out for how to effectively set up a Cassandra cluster, and it's many, many, many pages. But one of the recommendations is to distribute your nodes into at least 3 availability zones, and have one node with the Spark master, Spark slave, and then a Cassandra, and this is another variation, seed node, and then in one availability zone, and then the other 2 have a Spark slave and Cassandra seed node. Now, what a seed node does is you only need one of those per availability zone, and then I can add as many nodes as I want underneath those. When each of those nodes come online, and this is done really easily by packaging up an AMI and then just spinning up a new instance of it, the Spark slave will need to know where the master is, and it'll talk to the master and get itself wired up. And then the Cassandra will look for one of the available seeds and then bring itself into the cluster. And so the seed is, while there's no master nodes in Cassandra, there is this notion of a seed, and that's just there to help get the clusters started up. So because Spark is pretty CPU and memory heavy, and Cassandra is also CPU and memory heavy, and extremely disk heavy, as you can imagine, because it's actually got to write stuff, you're going to need some hefty instances per node. There's an interesting discussion to be had about the balance between how many nodes should I have versus how big should I make them. Right? If I have a bunch of really small nodes, it's much faster to bring a new node online because there's less data to shuffle around, but it's more things to manage. Yeah, it's a trade-off. So building these 2 tools, there's a very common pattern for setting up a data pipeline. I have some sort of data source. I read that, like a Kafka or a Rabbit, I read that data off the pipeline, and then I save the data into my cluster, and then I run a little batch processing job or what have you to turn the data and then save it into still another relational data store that the end user will actively actually query. It's generally considered poor practice to query the cluster directly. It's there's a lot of overhead with it, spitting out the data amongst all the clusters and doing its calculation and then sending it back to you. So while it's fast, there's still a lot of network traffic, and your day-to-day usage, your real-time querying is ultimately better served by an actual relational data store. All right, coming down to the wire here. So what's it like to actually work with these 2 together? And specifically, what are my options as a Spring developer? Now, you might immediately think of Spring XD, although that's being, I believe, phased out in terms of to be replaced by Spring Cloud Dataflow. Both tools allow you to set up data pipelines pretty easily, especially if you saw the talk that was on before me. You can wire up message queues like Kafka or Rabbit as data sources, dump information into Cassandra, and all you have to do is build some classes that know how to pipe the data back and forth. But we didn't end up going that route. So we thought our data was a special snowflake that was special and didn't need something like that. But we also wanted to take full advantage of the Spark and Cassandra connector, and our pipeline is pretty minimal. And our programming, the programming model of these 2 together is pretty easy, which we'll see in a minute. So this is a diagram of our setup. It looks very similar to the last one we saw. We have a Rabbit. Our data comes in off of Rabbit. We have a small Spring app that is watching for those changes and then performing, gathering the data it needs to read if there's anything beyond with the data that came over the wire, and then it saves it to Cassandra. And then it also, after it's finished writing, it will periodically execute a job to process some of the numbers that we just fetched, and then store them into a Postgres database, which the end user ends up seeing. Although, and that little dotted line there is that we sometimes will query the thing in real time, because it is pretty fast. But don't really do that. So, coding Spark and Cassandra. So some of the objects you'll see coming up, you'll see the Spark configuration class. There's again the Java Spark context, which is a Java implementation with a regular Spark context, which is itself a Scala class. There's a object called Java functions, which is an adapter towards from Java into some of the Scala code that Spark has and that the connector gives you. And then there's some mapping functions that allow you to perform operations back and forth to basically take a in-memory class and then write it to Cassandra and back and forth. So setting up a Spark configuration is relatively easy. There's an example of a demo coming up. You can see I basically just set a Spark configuration, new Spark, and then two interesting bits there I set up, and I basically tell it where Cassandra lives. And I can choose any host and just put it there. But in production, you're basically generally just going to put localhost, which is interesting because it'll just talk to itself. And then I set its deploy mode to be what's called a client. One other way to run Spark is to actually submit a jar into the cluster itself, but it's not as fun. And then I take that configuration file and generate my context with it. And then one interesting line here. Right below that, the add jar line. We'll get into why that's confusing in a moment. And it's hinting at one of the most difficult bits of working with Spark. So the Spark configuration offers countless configuration options. Some of the ones that we found useful are the ones where you can manage your resources. So I can set the number of cores and the number of the amount of memory that I give each of the executors that Spark will start up. And another hint, there's a way where you can tell it packages and repositories to fetch code. Now, I show this slide because one quirk that Spark has, again, it's designed by academics, is that if you want to work with localhost, or there's a variety of different ways to tell it which Spark master to talk to. And it's an overloaded string value. So if I say my Spark master is local, it's going to start up a Spark automatically standalone and use just one thread. If I say local star, it's going to spin up a local Spark on startup and use up all the threads on my system. But if I give it a Spark : / it's not going to start up anything and just make a connection. It's going to use that Spark command tells it to use, it lets it know that it's going to be using Spark's built-in cluster management. If you don't want to use Spark's cluster management, you can also, of course, use Mesos. There's an adapter for Mesos, as you would imagine. So then this next slide demonstrates the Java functions class. So I have to give it the context, and then Java functions gives me a variety of additional methods specifically related around Cassandra that I can work with. So in this case, I've got my Java functions, I pass it a context, I then immediately say Cassandra table. So now I've basically mapped an RDD to my Cassandra table, or the other way around, rather. I have a Cassandra table that's now become an RDD. And if I don't specify anything further, it's going to suck the entire contents of that Cassandra table up and just split them out and distribute it out amongst all my nodes. So immediately after that, I execute a where clause to filter the information before it comes out on the wire to basically say, okay, well, I know I have a huge amount of data distributed out. I just want things with this particular symbol in a particular year and a particular date. That MapReduce is an example of the mapping functions. So what it's really going to do is to take every row in that Cassandra table and turn it into a POJO called daily price record, and then I can work with it in memory. It's all very nice. So a bit of a warning, which we'll get into. You'll almost certainly need to dedicate at least one full-time engineer to managing the Cassandra cluster. This can be a non-starter for many startups. It's impossible to devote that much engineering time to a data solution unless you absolutely have to. There are some handy tools to help you monitor your cluster. So DataStax, again, offers has a tool called Ops Center, which is very nice. They have a limited version that you can use for free on your cluster. There's a company called Instant Cluster that'll manage it for you if you're willing to pay a premium for that. Another consideration, running your Spark cluster will likely be very expensive, depending on your setup. Spark and Cassandra are designed and encouraged to be used on commodity hardware, for example, standard AWS instances, but they're both resource hogs. So at a minimum, if you're on AWS, you're going to want an M4X large per node, which can get kind of pricey. And if you can, go larger. C4 is also a very good instance type. Another recommendation that they recommend is to buy instances that have solid state drives as opposed to your standard elastic block storage, which can also be, very pricey, and it all adds up. Like all of our main services run on T2 smalls, and our Cassandra cluster is these massive M4 things that sit in a giant ring. It feels a little bit lopsided. I don't know. Okay, so the most difficult part about working with Spark is fundamentally understanding where my code lives and where it gets executed at runtime. So what's tricky about this is that most examples you'll find when looking for hints on how to work with Spark all have the same demo, where it's load a file and do a word count on the file. But it's all done locally, and it's all very trivial. The interesting bit here is that if I want to start getting advanced by mapping into classes or doing something more than just summing the contents of a RDD that contains a native Java class, I have to understand exactly where the daily price record object lives and where the symbol results.map.collect is actually getting executed. So you write the code, and it looks like it's part of your client application. But what Spark is doing is taking all of that code and then shooting it out to each of the Spark slaves on startup. So when I submit a job that says, hey, map everything into my daily price record class, it doesn't necessarily have that. All each of the slaves see is just the map and collect functions. And then there's some sort of class in there called daily price record that they have no knowledge of. So it's a class path issue. So each of the nodes, they just have whatever the default on the objects that come with Spark. So in this case, Spark, Jackson. My Spark master or my client node has all those, but it also has the local code that I'm executing. So all my local packages, including the one that contains daily price record. So when I shoot the jobs out, all the other nodes go, great, I'll execute that, and then they fail because of a class not found exception. So how do you fix that? And that goes into this demo. So I've got 3 minutes. Let me sorry, should have practiced this. Where's my mouse? Can't find my mouse. There it is. Okay. Mirror displays. Here we go. Okay, so here is a small Spring app that I've broken down into two packages. So this is a Gradle build that contains two sub-projects, one called Spark Shared and one with my main client code, Spark Spring Demo. Just a little bit of setup. If I go, I'm gonna start up Cassandra because it takes a second or two to start up while we talk. And the demo itself is standard Spring app. I apologize if that's a little small. I'm not sure how to increase the font size on my project window. The basic folder structure is a standard Spring app. I start up my class. I've got a config section. I've got my basic, I've got a bean config for my Java Spark context. You note that I'm injecting values from a configuration that, I can set my Cassandra host to be configurable. So when I'm working in development mode, I'll likely end up setting my Spark master to just be local, and I'm giving it 2 CPUs to work with or 2 threads to work with. And then my Cassandra is just, I'm using a key space called stock data using my connection host. But if I were in production, I might have something like one of my nodes that is running in my cluster, and then an actual Spark master URL. So Cassandra's up. So if I look at, so they give you a nice command line tool where I can go in and I can select from. Oh no, hold on. I'm going to show you some of the data real quick. I'm running out of time here. Describe key spaces. Oops. Oh no. I can see I have stock data. Describe tables. I can see I have one called company. Oh, what? Oh yeah. Company. I'm getting nervous, so I'm messing up. So you can see I have a bunch of companies saved in this table here. And then daily price record. And I have a relatively big amount of time series information in here that's all keyed by symbol. So you can see the symbol on the left, year, and then a bunch of information representing value, percent change, daily stock movement. I should probably point out that this is a demo web containing stock information. So if I want to run my app, I basically am doing a Gradle multi-project build where I will Spark shared, and so this is a sort of a common development thing. As I make changes in my shared library, I'll publish at local so that the changes get pushed, and then at the same time execute my little app here. So that's going to start up. It's going to rebuild my little shared library that contains all of the code that actually gets executed by Spark, and then it will actually start the client application, which is going to make use of the information. So I'm running out of time here, so I'll just show you just one quick thing, and then I'll be done. Localhost. So after that's booted up, I go to 8080, and then I query for API/stocks. And so you can see that took a little bit of lag to actually do, and it's still a localhost query, but it shows you a little bit that Spark takes a little bit to warm up and do a bunch of things, but it's very powerful in the end. So what I had it do was go and look at all of those records that you saw, every single one of them, and find for each symbol within the past 30 days, find the low value, the high value, and then the average of the volume in terms of the movement of the stock. And what that looked like was, so I created a separate project that contains pogos like the daily price record. Those get sent out to all the different nodes. And I've got this job that runs. It grabs all of the company information and then creates a key value pair. So this is what's called a pair RDD, and then a pair RDD of the symbol and the daily price record. And then it's joining those together, because I can't do it on the Cassandra, so it's able to take the company information, slap in the name, and then do a roll-up of all the information. Unfortunately, I'm out of time, so I can't run through the rest of this, but I'll send out these slides. I have a link. There's a lot of comments in here. If you're curious, you can step through and see sort of how each of those steps was done. So with that, I am going to say thank you. I don't think I had time for questions, but I will happily talk about this for longer than they'll let me, as I've just done. Thank you all for coming.